Hi, let's talk a little bit about Kirchhoff's laws. We're going to start off by talking about Kirchhoff's current law, but to understand Kirchhoff's current law, we really have to understand the concept of a node, because nodes are essential to understanding Kirchhoff's current law. A node is not very complicated, but it is an important concept. A node is simply any point in the circuit where two or more circuit elements connect to each other. So you could think of it as like an intersection in a road. Here you can see an example of a circuit that has three nodes. And it turns out that being able to identify the nodes in a circuit is a very valuable skill. One piece of advice that I would have for you is just simply try to identify all the wires that connect to each other without passing through any other circuit elements. And so you can see here I've tried to indicate that the top left corner is all one node. And then over here we have the top right corner is all one node. And then on the bottom, we have that the bottom is one entire node. And so you can see there that by trying to identify connections amongst all the wires that have no circuit elements in the middle of them, we're able to identify the nodes. So that's a good shortcut for trying to figure out how many nodes are in a circuit. Being able to figure that out will become a very valuable skill to us later on in this course. Now, there's two other definitions that are valuable. First of all, a junction. A junction is a node where three or more circuit paths meet. So you can see up here an example is a junction would be right here. This is where three or more circuit paths meet. And another one would be here. Actually, there are a lot of junctions in this circuit. There are 4 of them. So I'm identifying those 4 junctions up here. But notice that the junction is just a single point, that the entire node it can extend much further than that. And you could also identify, for example, a corner as just being a node where only two circuit paths meet. One other thing to remember is that the voltage source and each of the 4 resistors are called branches. And a branch is just simply a path that connects 2 junctions together. And so you can see that there are branches and there are junctions in the circuit above. But why do we talk about nodes? Why do we care about nodes? Because of Kirchhoff's current law. Kirchhoff's current law is one of the 2 most important laws, well, let's say one of the 3 most important laws in all of circuit analysis. And it simply says that the sum of the currents entering a node has to equal the sum of the currents leaving the node. So that kind of makes good intuitive sense. If that weren't the case, then one of 2 things would have to happen. Either there would have to be charge building up at the node, or there would have to be charge leaving the node. Now, in either of those cases, we're going to find that there's going to be either some new negative charges building up at that node, which will increase the voltage of that point and will thereby reduce the likelihood of any additional current flowing into that point, or there'll be charge moving away, which similarly will eliminate the possibility of current flowing into the node. So it's possible over the course of a very brief period of time, maybe femtoseconds, that we could see that there would be a net current entering or leaving a node. But over the course of the amount of time that we work with, that's just simply not going to be the case. So here you can see an example of a node that has 2 currents flowing in, I1 and I2, and then there are 3 currents flowing out, I3, I4, and I5. And so we can write an equation that puts all of the currents that are flowing in on the left and all of the currents that are flowing out on the right. And so that's going to allow us to identify Kirchhoff's current law for this particular circuit diagram. Now, there are 2 other ways of writing KCL, some of which are preferable in some certain circumstances. They can be quite valuable. One of them is if you identify that there are only currents entering the node. Then you can simply say, well, if there are no currents leaving the node, then the right-hand side of that equation must be 0. So I can just write that the sum of the currents entering the node is equal to 0. So you could actually redraw the circuit from figure 2. So this is the figure that we just looked at. Notice that this has 3 currents leaving the node. So I'm going to simply redraw those as currents entering the node. Now to do that, I have to, of course, add a negative sign, because what I just did was I reversed the direction of the current. There used to be arrowheads underneath these X's that I've hidden now. Those arrowheads were flowing out, but now they're flowing in. But I have to write negative I3 and negative I4 and negative I5. So now I can rewrite the equation as I1 plus I2 plus negative I3 plus negative I4 plus negative I5 is equal to 0. Now, if you're more comfortable with this form, that's great. Notice that it is algebraically equivalent to the previous one, because the previous example said I1 plus I2 equals I3 plus I4 plus I5. All we did was really move those terms over to the left-hand side of the equation. And you can probably guess the third form simply says that the sum of the currents leaving the node is equal to 0. And there the currents entering the node are equal to 0. So all I did there was I redrew the 2 that were entering the node as now leaving the node. So we have minus I1 and we have minus I2. And so here you can see minus I1 plus minus I2 plus I3 plus I4 plus I5 is equal to 0. Algebraically, all we did was to move those two terms over to the right-hand side of the equation, but in practice, what we did was we summed the currents that are leaving that particular node. So at this point, you should have enough information to look at the Kirchhoff's current law example problem. I would encourage you to do that, and then once you've checked the solution, come back and talk to us.